Hi everyone and welcome back. In this video, we're going to talk about the system design of the Dropbox. We're going to start with the high-level design of the client side and the server side, how they communicate with each other. Then we're going to talk about the last cycle of the file. We're going to talk about how it's created locally, how it's broken down into the chunks or blocks, then gets synced with the remote servers, how all this data propagated on the data side as well as the metadata side, and just drill down more in the components of the backend system. We're going to talk about the queue, the sync service, the data stores that we're going to use, as well as we're just going to walk through the exact workflow on how the sync of the files happening on the backend. With that, let's get to the video. Let's start with the high-level design just to understand the main components and overall design. So as you can see on this diagram, on the left of the load balancer, we see the client side and all the components that would exist locally to the client. It would be either the desktop application or web client or anything else. And on the right side, we see the components of a V at the backend and how the system would be implemented behind the scene. So to understand it, let's walk through the main workflow. We have a client installed on our desktop and we create a new file. As you can see on the diagram, there's a green box that says the user. So this is the user who creates a file or something on the file system. So we simply, let's say, copy paste the file to our Dropbox folder. Luckily, we have 4 different components. We have a watcher, chunker, indexer, and relatively small metadata DB that can be a simple MySQL database that would be storing the local state of our files, blocks, and directories. So high level, when we create a file, we have a watcher that watches the directory of the Dropbox. Once there is a new file added or modified, the watcher will know about it and let the indexer know. Indexer is a service that receives data from the watcher about any new files added, changed, or deleted, and then it does multiple things. First, it breaks down the file into the chunks, if it's a newly added file that was added, and then it uses that chunk information to update the local database. Because any changes in our file system or a Dropbox folder should be reflected in our local database. So let's go through an example. For instance, we add a new file. As the file is added, Watcher sees that file. It sends it to the indexer saying, hey, there is a path for the new file that was just created. Indexer sends this location of the file to Chunker. Chunker would break that file into the blocks. In our case, we would be using 4 megabyte blocks, and this is what Dropbox actually using. So the Chunker would break it down into the 4 megabyte blocks and then send that information to the MetaDB that would be stored in there with the chunks hash and file data. And as a result of it, they would have a new record in our files table, and then they would have multiple records where every row would consist of a checksum of the block and then the reference to the file that this checksum is a part of. Now the next use case, what if we update the file? So what we would like to have is file versioning. And if we didn't use blocks, then to keep that file versioning for a file of 1 gigabyte, we would need to store multiple 1 gigabyte files, which is not what we want. Ideally, we want to support versioning and also minimize the amount of extra storage that we have. So with the notion of the blocks, as you can see in this example, for instance, we have a file that is split into 5 blocks. Then we make a change to the file, and turns out that that change ends up in the block number 3. So what we do, we keep the rest of the blocks as they are, we are not touching them, and the new version is only created for the block number 3. So in our database and file system, we would have 2 blocks of 4 megabytes. One is for the version 1.0 and the other one for the version, let's say, 1.1 of that specific block that is number 3. So the overhead of the update in this case would be 4 megabyte instead of, let's say, if the file was 1 gigabyte, it would be 1 gigabyte. So what did we learn? We have a Dropbox folder where we drag and drop or copy files. Those files are split into the 4 megabytes blocks. And those blocks are immutable. They never change. If we change the file, all we do is just identify the blocks that were changed, and then create new blocks was the next versioning of that file. This way, we can support version. We can always roll back because we have the previous and the current version of the block, and we can reconstruct the multiple versions of the file. At the same time, we have a very low overhead on the file system. All the version information would be stored in our local database that would maintain a mapping between the files and blocks and different versions of the blocks. This is how the local client would look like. But the problem is that if we delete this data, everything is gone. So we need to make sure that this state is also stored on the remote server in the Dropbox, and we can always download it from the server and reproduce either it's on the phone or a computer or anywhere else. We have two main types of data. The first one is metadata about the files. These are file names, block, checksums, the markings between them, versioning information, and other metadata. And the second part is the file data, actual bytes of the files or bytes that blocks consist of. So on the remote server, we would have the block storage service where the blocks would be transferred and downloaded from. We would have a metadata service where all the blocks information would be stored. And we would have a sync service, the service that would work together with the notification service and be responsible for making sure that once you make a change, they change not only makes it through the remote server, but also all the people that subscribed that or have access to the file that we just changed can see that on their local clients. So now let's extend our workflow with the server in play. So following our original workflow, as the file was added and local database was updated, the next step is that we would send all the newly created blocks to the block storage service. Once the data is stored, we update the metadata service by sending a metadata about the change to the remote system that would probably come to the same global queue or regional queue, and from there would be processed by a multiple services that would consume it, check the presence of those blocks in the block storage, and then if they exist, we would update the metadata on the service, and then that change would be propagated all the way through the sync service and then notification service to other clients. As you can see on the diagram, the workflow comes through the incoming queue, then it is stored to metadata, and then propagated through the sync service, notification service, all the way to the clients. And the watcher of the other clients would receive a notification from the remote service about the change that happened on that client files. And then the data would be sent to the indexer, the metadata would be updated, and the block data would be downloaded from the storage service. This is how a Sunny-based scenario would look like if we had no network issues, no service issues, or anything else. The biggest complexity here is how we exchange data between the clients and the servers. How can clients make sure that the server is updated almost instantly and other clients also get those details propagated? So as we update data on our local file system, first thing we do, we identify those new blocks and we send them to our block storage service, because this is the heaviest operation and we want to do it before we commit the changes at the metadata level. Because we can start to send those data and then something doesn't go right, it breaks down, so we don't want to have inconsistent state. So instead, first we upload the blocks to the remote system, and only then, once that is confirmed, we send the metadata to the remote system to make sure that remote state gets updated. Through number 5, we go to the incoming queue. And this one, usually called global queue, but in reality, it's not really global queue. It's more of a regional queue that is responsible for making changes to the users who have their data stored in that specific locality. You can think about it as we can have separate queues, and one can be in Europe because of the GDPR and European data rules. The other one can be in the United States. The other one can be elsewhere. So we would have users pinned to specific localities, and then there would be a local incoming queue would receive all the changes for the users that have data in that region and process them. On top of the regional, we might also have multiple queues for different users. For instance, free users and paid users might have different queues, and we can have different guarantees. So anyway, the commit request comes through the incoming queue, and then it goes to the sync service. What sync service is responsible for is making sure that for this specific commit, the data exists and the commit gets stored into the database. So the system acknowledges that data is stored, the state is consistent, and we can get this propagated to other users. So to do that, Ferrest Sync Service would ask block storage for the blocks that should be committed and confirm that those blocks exist. And then it would store the metadata for those blocks into the metadata service and the database. Now, as they stored in the block storage and the metadata storage, it's time to make sure that it gets propagated to all the users. So the last step is that the sync service would send those metadata changes through the notification service to other clients. And other clients would receive it on the watcher, process the change, download the data from their block storage, apply the metadata to the local metadata DB, and have their local database updated. Now I would say the files we are working on locally is shared with 100 people. So when we make changes to the file, we need to make sure that that change gets updated on the remote server and also gets propagated to all the people that also have that file in their Dropbox folders. There are multiple methods like using the WebSockets or using the HTTP long poll. So we spoke about the WebSockets implementation when we talked about the Google Docs, real-time collaborating platform. We also spoke about the WebSockets when we discussed the system design of the messaging app. In our case, multiple methods can be used. If multiple people work on the file actively and connected to the Dropbox system, then we might use WebSockets to make sure they get those changes immediately through the notification service. But if it's something they just on the standby, then we can just use a HTTP long poll request to the remote server and just wait until those changes made it to the service and then get received by the clients. So two methods, WebSockets and HTTP request long poll, that can be used to pull the changes from the remote server. Well, this is it for this video. In the next one, we're going to talk about the block storage implementation and design that Dropbox uses for their backend services. So stay tuned, and I'll see you in the next one. Bye.